any 2 points in the set is within the set. Yeah. And those are important. There's a whole theory of convex sets and so forth. Yeah? Question? No? Yes, sir.
Just to reiterate,
Yeah.
the star-centered set is where you can draw from points.
The star center, yeah.
Yeah, the star-center point, whatever you want to make it, to any other points in the set,
Right.
such that the path is still a subset of the set you're working with.
Correct, yeah, yeah. Yep, that's it. All right, so that's kind of it for topology. I don't want to make too big a deal of limits in here. Like, we need to use them. I ask you to have some homework problems on them, but let me just keep it relatively low key in here in terms of like, this is not what the course is focused on, but it is something we can talk about and you have some homework on it. But so first of all, we say Zn goes to, let's say, Z, all right, as n goes to infinity if for each epsilon greater than 0, there exists big N in the natural numbers such that little n greater than or equal to big N implies that the modulus of Zn minus Z is less than epsilon. So this is the definition of convergence for a complex sequence. If you remember from Calculus 2, this is exactly the definition for convergence of a sequence you should have seen there. And if you didn't, sorry, but there it is. So just this is modulus now. Theorem. Zn goes to Z plus Z equals to x plus Iy if and only if xn goes to x and yn goes to y. So we have this theorem. A complex sequence has a limit if and only if its real and imaginary parts, both separately, have a limit, like that. So that's a nice theorem we could prove if I had more time. I don't. Another thing I should tell you about is that there's such a thing as a Cauchy sequence. So if for each epsilon greater than 0, there exists big N in the natural numbers such that whenever m and n are greater than, I should say m and n are integers, and m and n are greater than or equal to n, we have that implies that the modulus of, let's say I guess I'm using z's. Let me use z's. Zm minus Zn is less than epsilon. All right. Then, if all of this is true, then this sequence, Zn, is a Cauchy sequence. So a Cauchy sequence is one for which you can make the difference between elements far out in the sequence as small as you like by simply going out as far as you like. That's a Cauchy sequence. If each Cauchy sequence converges, then the set is said to be is complete. A complete set is one for which Cauchy implies converges. One of your homework problems is to show that the complex numbers are complete. Now the way to do that is basically, it's very much related to the help I got earlier today. So essentially you're looking at something like, Zm minus Zn, right? So let's think about this. This is like a little hint for the homework how to think about it. So this would be like xm plus xn, minus xn, right? Plus I times ym minus yn, right? If you had a complex sequence, you could look at its real and imaginary parts like this, right? And then this would be less than or equal to the, absolute value of the difference of the real parts and the absolute value of the difference of the imaginary parts. All right? And that, the thing is, you can control these. Why? You can control those because you know that the real numbers are complete. So if you have a Cauchy sequence of real numbers, it automatically converges. This is known from real analysis. So we can use that result to prove completeness of the complex numbers pretty much because of this estimate. Right? But anyway, I'll help you more with that if you get stuck on it. I understand, it may be intimidating at the moment. That's fine. So that's pretty much it for sequences. The properties of sequences still hold, like limit of a sum is the sum of the limits, the product theorem, all that stuff, all right? So next up, we talk about definition. What's the limit as z goes to z naught, f of z, right, is equal to L for z naught a limit point of the domain of f. We can define that, all right? How do you define it? Is defined as follows. If for each epsilon greater than 0, there exists a delta greater than 0 such that 0 less than modulus of z minus z naught less than delta implies the modulus of f of z minus L is less than epsilon. In that context, we get to write that limit equals what it is. Yes, sir?
Is the domain of a function f a complex domain?
Well, yeah, we're talking about complex functions. It's a subset of the complex numbers. Yep. Yep.
And thus is always open and connected?
Oh, no. That's a different use of the word domain. So, yeah. Good question. So it is annoying, but it is true. There are two different uses of the word domain that happen.
Of a function
Domain of a function.
from a set being called a domain.
Yes, a domain may or may not be a domain in the topological sense of the word. That is a good point. An annoyingly necessary point given our vernacular. Sorry, it is what it is. What would it mean for a function to be continuous? Yeah? F would be continuous at z naught. What would I write? We simply write the limit as z goes to z naught of f of z equal to what? If f is continuous at z naught, what do we write here? For f to be continuous at z naught has to be a point in the domain of f. It can't just be a limit point. It has to be a point in the domain of f. And this simply has to be f of z naught. All right? Now, in my notes, I have the analog of this theorem for a function. See, the limit, if you have the function, remember we've been finding last week, like f is equal to u plus iv. Remember that? So the limit of a function, guess what? It's the limit of the u part plus I times the limit of the v part. And if those two both exist, then the limit of f exists. And if either one of them fails, then the limit of f fails to exist. So we have a choice, right? We can either talk about the complex limit of f of z, or we can talk about separately the limit of the real part and the imaginary part. And if you study limits in the plane, in the two-dimensional sense, this is exactly the usual definition of limit in like calculus 3. These are the kind of limits that come in from every different direction. They're not left and right. They have to consider all possible directions. So there's all kinds of conniving counterexamples where you can have all kinds of nice behavior along lines, but then if you study parabolas, all of a sudden the thing's ripped, you know, and not in the good way. Sorry. I'm afraid I have a son who's becoming a musclehead. I don't know. Let's see here. So let's look at the proof of the theorem I'm talking about. The limit laws. Do you guys remember limit laws? Limit of the sum is sum of the limits. Limit of the product is product of limits. You can pull a constant out. All that jazz. So those things still all work here. And you know what? The proofs of those things are actually still the same proofs. Like every proof I could make almost without exception. There's one major exception. The proof that I give in calculus 1 for proving limit laws, where I have to deal with, you know, absolute value, I can give those proofs here, except with
The modulus.
exactly. So let's look at some of those. Although first I'm supposed to look at this. I should probably mostly look at this. Tell you what, we're just going to look at this. Next time I'll start with limit laws so we can relax, all right? Next class I talk about the theory of real differentiability on the plane. It's actually like pretty simple. So essentially I'm going to describe to you there's something called the Jacobian matrix. You can calculate it, it's just some partial derivatives. It's very easy. Yeah?
Just quick question.
Uh-huh.
What are the limit laws around computation? Because that's pretty much the only thing we ever see on the topic.
Well, I think if we understand this, then we can do that. So let's see here. So if we have f as u plus iv as complex function, and that's a limit point, and we have that the limit of f is L1 plus I1 L2, I'm claiming that's true if and only if the limit of u is L1 and the limit of v is L2, all right? So I'm going to prove the converse direction. I'm going to assume that this and that are given, all right? All right, so assume those limits exist. I will select delta 1 and delta 2 such that the distance being less than delta 1 implies I'm within epsilon over 2 for the u, and I'm within epsilon over 2 for the v, respectively, for these choices of delta. I want to have my cake and eat it too. So I choose delta to be the minimum of both of them. That means if I have z that's within delta units of z naught, I have both of these estimates. So when I look at the distance from f of z to L, which is this, I can use a triangle inequality. Triangle inequality, of course, modulus of I is 1. Lo and behold, epsilon over 2, I get epsilon. So I have proved that f of z minus L is less than epsilon, so given that z is within delta units of z naught. Therefore, by the definition of limit, I've proved that f of z goes to L1 plus IL2 as z goes to z naught. So one of your homework problems is to reverse this proof, to assume that you're given that this limit exists, and you're trying to prove these two limits exist, all right? It's, again, based on the inequality Ben pointed out earlier today. It's all about that modulus of z is bigger than or equal to the real part of it, bigger than or equal to the imaginary part. That's kind of, I think, the linchpin there. But anyway, to answer your question, I think like z conjugate is f of z equals to z. So f of z equals to z conjugate. That's x minus iy, right? So here we have u of xy equal to x. We have v of xy equals to minus y. Are these continuous functions? do the limit of those exist on the complex plane? They sure do, right? So you can prove the limit as you approach any point of this is just that point, is that the x value of the point. Likewise, the minus y value of the point. By that theorem, then the limit of the complex conjugate of z exists, and it's equal to exactly the complex conjugate of the limit point. So yeah, we could prove it. Listen, you could do epsilon.
Or the conjugate of the limit could be.
Yeah, there's an easier way. We could just do epsilon delta proof. Let epsilon be greater than 0. Choose delta equal to epsilon. You can prove that the complex conjugate's continuous at an arbitrary point. That would have made a good homework problem. Why didn't you ask me this last week when I was writing your homework?
Darn.
Oh, man. You have other problems, though. Like, on the homework, I'm not, like, making a personal comment. But
Let me rewrite your website and ask for them. We'll talk.
sorry, I messed with you guys, because I love you.